Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about AC phase and power factors in RLC circuits. To get into this particular subject, we need to recall some things from our previous video discussions. I think that the relevant things to recall here are what we've learned about reactance and impedance, and what we've learned about phase relations and phasors. So first we recall that reactance tells us the ratio of peak voltage to peak current for a circuit element or device, and that reactance then goes to impedance, which tells us this same ratio but for the circuit as a whole. This impedance, of course, is just the square of the difference between the inductive and capacitive reactances plus the square of the resistance, and then square rooted, or in other words, it is the square root of omega L minus 1 over omega C quantity squared plus R squared. And again, this ratio that we're talking about here is the peak voltage divided by the peak current. So that's the first thing that we need to recall. The second thing that we need to recall is about phase and phasors, represented often by this little mnemonic Eli the Iceman. Again, voltage leads current for an inductor, current leads voltage for a capacitor, current and voltage are in phase for a resistor. The phase factor, phi, basically ends up being plus or minus pi over 2 or 0, depending on if you have a resistor or a capacitor. And all of these ideas, both the impedance and the phase shifts, can be represented by phasors and phasor diagrams, or a phasor diagram for the circuit. The phasor diagram then is just sort of the diagram that shows the phasors for all three elements within your circuit, and these elements are represented each by a vector-like arrow, the length of which is the peak value of the voltage, and then the projection onto the y-axis represents the instantaneous value of the voltage. These phasor arrows all rotate together within the diagram with the same angular speed, or angular frequency if you will, given by omega, which is the omega in this current. So 2 pi times whatever the cycle frequency of the current is. So with all of those things said, we're ready to start discussing today's topics, which are, again, the AC phase or phase angle, and the power factor in the RLC circuits. So we will do that and also maybe briefly discuss resonance. Now there's a second thing that we can define, and it's maybe worth redrawing our phasor diagram for an RLC circuit generically. And that second thing that we can define is what's called the phase angle for the circuit. And so, like, let's say that our circuit is such that this right here, this first arrow, could represent our current at a given time. So this is I naught. That means that at that same time, the voltage drop across the resistor, VR, would be represented by this second arrow here. And it means that our voltage drop for the inductor and for the capacitor are going to be represented by this pair of arrows that I'm going to draw here, VL naught, and then for the capacitor, maybe VC naught. So VC naught. Note that VC naught plus VL naught would be maybe this arrow right here. So let's draw an arrow. I'm just offsetting it a little bit for visibility purposes. So this is V L minus VC. All right, that means that our overall for the circuit sort of voltage, our power supply voltage, if you will, is this vector right here, or this phasor right here. So this would be V, variously called V naught or VS naught. Okay. Now, there is going to be some angle phi between the voltage across the resistor and the voltage across the source, assuming, of course, that we have a capacitor and an inductor and that our omega is non-resonant. When it's resonant, then VL naught and VC naught actually will add to 0, as it turns out. So you can figure out what's the resonant condition just from that. Basically, if the voltage across the inductor and capacitor are both equal in peak, then the output voltage from the source just matches the voltage across the resistor. That's sort of the consequence of this, because the other two will have canceled out, or this little VL 0 minus VC 0 arrow has a height of 0, in other words. Using a little bit of geometry here, so you could even call it like right triangle geometry. It should be obvious that the tangent of the angle of the phase angle phi naught should be the opposite, which again is V L naught minus V C naught, divided by the adjacent, which is V R naught. Now, in terms of the current and of the reactances, this ends up being the reactance of the inductor minus the reactance of the capacitor divided by the resistance. There's a I naught term on both top and bottom that cancel. Also, perhaps useful would be the cosine of this phase angle. The sine of the phase angle could also be used, but very often it's the cosine that's given. The cosine should be the adjacent divided by the hypotenuse, and this hypotenuse, VSO, is the I naught times the impedance Z. So what we'd be looking at for this cosine of the phase angle is the voltage across the resistor divided by the output voltage, which in turn is just the resistance divided by the total impedance of our system. This leads me to kind of the final concept in today's video, which is what's called the power factor of the circuit. The power factor is just telling us how much power is being dissipated by the circuit, or in other words, how much energy is being lost per unit time within the circuit. To consider power factor, we need to recall a couple of little things. The first is that inductors and capacitors don't dissipate power, only resistors. The second thing to recall, or if you count this as two things, I guess the third thing or the second part of the first thing to recall, however you want to slice it, is that power dissipated by a resistor, generally speaking, is I times V, but we usually switch that over to I squared times R. So in the case of an RLC circuit, the power dissipated, we might look at average power since we're looking at an AC signal. Thus, we're looking at, for current, the RMS current. And so, in some sense, we would say something like P average is IRMS squared times R. But we want to do this in terms of the impedance of our circuit and of this sort of phase angle. And so, in terms of those things, the average power being dissipated, again, you can use IRMS squared. That should actually be 1/2 I0 squared for what that's worth. Looking at this phase angle, if I want to get R isolated from Z, R is Z times cosine phi. So this ends up looking like I RMS squared times Z times cosine phi. And that duplicates for me the other equation that I had before with DC power and an ohmic resistor only. Alright, so last little point before we move on to our example. I started this by saying we're talking about power factor. I ended this slide so far by talking about average power dissipated. So where's the power factor actually come into play in all this? Why am I not just talking about power? This cosine phi term is what's sometimes called the power factor for the circuit. And so that's also why on this previous slide I defined a tangent of phi and I defined a cosine of phi, and I mentioned you could also do the sine of phi, but I didn't really work out the sine of phi. It's just not as interesting as the tangent and as the cosine in this phase diagram. So let's go ahead and work an example or two, maybe a quick example of 2 parts. So given the previous RLC circuit, that is the circuit that I worked this example for before, what is the power factor and what is the resonance frequency for this circuit? Okay, so note that what I had previously found for this circuit was that the impedance Z was 63 roughly ohms. So I can actually write out more digits. It's not just 63 ohms. The calculation came out to 63.339032222 ohms for what it's worth, and we just retained 2 digits of precision. And then we have this frequency 120 hertz for which this was the impedance. So the power factor that we're looking for here would be cosine phi. And cosine phi, again, is given by R divided by Z. So that's 10 ohms, because R was 10 ohms before, divided by 63 point, let's say 3, etc. ohms. If I plug that into my calculator, I end up getting a power factor of about 0.15788. So let's call this a power factor of 0.16. Now note that a power factor of 1 essentially means that the impedance and the resistance are equal, and so we're dissipating a lot of power. And at the other extreme, if I have a power factor of 0, that essentially implies a very, very large impedance, or in other words, just 0 resistance. So I either have a lot of a large capacitive reactance or a large inductive reactance, or both, compared to the resistor, and so very little power would be dissipated. So this power factor is basically telling us what fraction of the possible power that could be dissipated is actually being dissipated. The other part of this question was to determine the resonance frequency. So remember our little aside here that resonance occurs when this angle basically is 0, when this voltage drop is from the supply is equal to the voltage drop across the resistor, which is the condition that omega L equals 1 over omega C. Now we've got an L and a C value kind of fixed. I'm looking at omega L is equal to 1 over omega C. That's the same thing as basically saying that omega squared is 1 over L times C. So that is 1 over 5.0 millihenry, so 5.0 times 10 to the minus 3 times 20 microfarad, so 2.0 times 10 to the minus 5 farad. And so that gives me omega squared is 1 over 1.0 times 10 to the minus 7 seconds squared. And so that basically means that omega is 1 over the square root of 10 times 10 to the 4 inverse seconds. If I want the frequency to be frequency f, then I got to divide that further by 2 pi. What I end up getting when I do that is about 5.0 times, or 5.032 times 10 to the negative 6 hertz. So that is the resonance frequency for my circuit. Alright, well that is all for today's video. You have hopefully learned something from watching it, and as always, thanks for watching.